Hi everyone. So this is going to be the recorded recitation video for April 6th. I have a few questions here that I was asked about that I'm planning to go over, 2 homework questions and then 1 from the practice exam. All right, so let's start with number 30 here from 4.5. So this is a true or false question. So what that means is if it's true, you write a little bit about why it's true. If it's false, you can use a counter example to demonstrate why it's false. So let's start off with part A here. We have, if there exists a linearly dependent set in V, then the dimension of V is less than or equal to P, and P is the number of elements in that linearly dependent set. All right, so let's break this one down. So we have some vector space of V. I think it may have defined that actually in the full question. So we have some vector space V, and we have a set of vectors in it. And we're being asked about how the dimension of V compares to the number of elements in this set. All right. So when you see these kinds of questions, intuitively, if you can make a linearly independent set, that says something about it. That says that you have this many linearly independent vectors in V. That tells you something about the dimensionality of it. How big is it? How many linearly independent vectors can you fit in it? Linearly dependence is a little trickier though. There's not as much you can say about it. It's pretty easy to come up with linearly dependent sets, and I'm going to show you one. So let's pretend that V, and this is usually good for demonstrating examples, is pretending V is one of your real number spaces. So I'm going to say, what if V is just V is equal to R3. So V is just going to be anything in that 3 space, R3. All right. And then we have a linearly dependent set here. So if this is true, if this statement's true, then if we make a linearly dependent set in V, it should have more elements than dimensions of V. Well, the dimension of V here is 3, right? Because we have V is R3, and we know R3 is 3 dimensions because it says it. So, all right, now we can think about this as, can we make a linearly dependent set with fewer than 3 elements? And I say, sure we can. Let's consider a linearly dependent set in R3 with 2 elements. There's a ton that you could make. I'm just going to do an easy one. Let's say we have 1, 1, 1. All right. And we need a second one, a second linearly dependent set. And I'll just say 2, 2, 2. Any 2 things that are multiples of one another, right? Those are linearly dependent. So now we have this linearly dependent set. P, which is the number of elements in it, is 2. V has dimension 3. And so we have something where P is actually less than a dimension of V, but we still have a linearly dependent set. So we have proven that that one is false. And that's your counterexample. Okay, let's look at part B now. If every set of P elements in V fails to span V, then the dimension of V is greater than P. Okay, so this, you can read it. It should remind you of thinking about bases and the idea of having a basis vector that spans the vector space, or a basis set of vectors. Essentially, you are guaranteed that you have at least one basis that spans your vector space and has the exact number of vectors in it as your dimension. So, all right, we know that we have some set of, and I don't know how many, but think about a set of vectors. There should be dimension V of these in here, right? Because we know that they're, we know that the basis of V, which is what this is, the basis for V, has dimension V, linearly independent vectors in it. And this obviously spans V. So this spans V. All right, and then it's asking us how this, if we can't come up with a set of P elements that spans V, basically there is no set, any combination of P elements in V doesn't span it, then is the dimension of V bigger than P? I'm going to say that's true, right? Because we've established here that if we can span V in some number of elements, then that is the dimension of V. And if we can't, then the dimension of V must be bigger. We must need more elements to span it. So maybe P is, I don't know, the first like 3 elements in here, and maybe the dimension of V is 5. We cannot come up with 3 elements that would span this entire space. We might need, in this case, 2 more. But basically the point of it is if you can't span it, then the dimension's going to be bigger. So this is going to be true. All right, and then finally part C here. So part C asks us if P is bigger than or equal to 2 and the dimension of V is equal to P, then every set of P minus 1 non-zero vectors is linearly independent. All right, for this one, I'm not going to tell you right off, but I am going to say, look at our first counterexample that we did and think about how that could be used here. Remember, we're talking about any P that's bigger than or equal to 2, and the dimension of V is equal to P. So think about that. Think about using that thing from part A. All right, moving on. We have 4.6 number 1. This is the question from the worksheet. Now I think, and I could be mistaken here, but I'm pretty sure the way that you're supposed to do this is each of these 1, 2, and 3 needs to be done for each of these for like 9 total questions. I'm not sure though, but we'll do that just to be safe and for practice. So, okay, let's start off with A then. So A asks us if the dimension of the null space of A is 4, then what is the rank of A? Okay. So, and let me pull up the text here. So we have some equations related to this that can kind of help us out some. We know that the number of pivot columns plus the number of pivot columns plus the dimension of the null space of A equals the total number of columns, which in an m by n matrix, the total number of columns, I believe, is n. So that's kind of your first formula. The number of pivot columns is also known by another name. I do not want a bullet there. Right, the number of pivot columns is also known by another name, the dimension of the column space of A. All right, so dimension of column space of A plus the dimension of the null space of A should equal the total number of columns. We also have yet another name for the dimension of the column space of A, and this is, just good for review of what all these concepts are, and that is the rank of A. So all three of these concepts over here are equivalent. All right, so we want the rank of A, which is, the same as the number of pivot columns, and which is also something that we can kind of figure out here using our equation. Right, so we have the dimension of the null space, it's 4. We have n, for each of these, n is provided to us. So we can say that the rank of A, which is the thing we need to find, equals n minus the dimension of the null of A. So there you go. And this is our equation that we're going to want to use. So like I said, there are 3 that we have to do for each of these. We want to do it when A is a 4x6, when A is a 6x4, and when A is a 4x4. All right, so let's do 1 for this one, and then maybe we'll go to B, and I'll leave you guys with the rest of them. All right, so A, we have a 4x6. All right, and remember, we're interested in the number of columns here. So the number of columns, remember, it's m by n, and the number of rows by columns, and columns is going to be 6. So our n in number 1 is 6. All right, and then our formula is going to look like 6 minus, and the dimension of the null space of A is 4 for all of these. And then the rank is just 2. So there's your answer. All right, and then for the rest of these, it's just you got to find n, plug it into the equation, and see what you end up with. All right, part B. This one asks us if the rank of A is 2, then what is the dimension of the null space of A transpose? All right, this one's going to take a little bit of thinking. So we're interested in the dimension of the null space of A transpose. Well, from what we know, dimensional A transpose, we could use this same formula, right? So this is just going to be plus the rank of A transpose. And what's that going to be equal, though? Because before, we said that the dimension of the null space plus the rank is equal to n. But here, we're talking about A transpose, right? So if you think about it, A transpose, so A had m rows and n columns. A transpose is going to have n rows and m columns, right? Because you're kind of turning it on its side. You're transposing it. So the total number of columns here isn't going to be n, it's actually going to be m, which is still something we can get from the original problem, but we just have to be careful with our numbers. All right, let's see what else we can figure out, because rank of A transpose, that's kind of a tricky one. Well, as it turns out, the rank, it equals the number of pivot columns, right? If you have, 1, 2, and then maybe one more down here, 3 pivots total, then you would say there's a rank of 3 for this matrix. Interestingly, though, the rank and the number of columns, number of pivot columns is actually equivalent to the number of pivot rows. Remember, you can't have 2 pivots in one column or row, so they're going to be basically the same. If you have 3 pivot rows, you're also going to have 3 pivot columns. And so we can actually say that the rank of, the rank is both equal to the number of columns of pivot columns, the number of pivot rows, and also then it is equal to the number of pivot columns and rows in A transpose, because that's just rotating it, right? You are switching rows and columns. So the number is still going to stay the same. So the rank of A is still going to be equal to the rank of AT. And that is the kind of crucial thing in this problem. All right, so if we do that, then all we have to say, and maybe I'll write this one. All right, so we're interested in null AT, the dimension of null AT. I'm just going to write at, what I mean there. This whole thing to be, there we go. And All right, so this is now going to be M minus rank of A, right? Because we're just subtracting over M minus rank of A. All right, and then this is just going to be a matter of using this equation for each of these. So we have one. I'll just do one. So A is a 4 by 6, right? So M is 4. So we're going to take 4 minus rank of A, which is 2. And that will give us 2 for our dimension of the null space. So you can figure that out for the rest of them. Just take M, plug it in, and get your rank. All right. Now for C, the last one. If A has 3 pivot entries, what are the dimensions of the null space of A, the column space of A, and the row of A? Okay, so let's work it out. Okay, so we'll just do part 1 again. So the matrix is a 4 by 6 here. All right, let's see. All we know is that A has 3 pivot entries. Well, that actually tells you quite a bit, right? If you have 3 pivot entries, then you know that your rank is also going to be 3. And you know that the dimension of your column space and the dimension of your row space will both be 3. So that tells us a lot right off the bat. Dimension of the column equals dim row equals 3. All right, and the only other thing is, what about the null space? So that's the part that's actually going to change from matrix to matrix here, right? We have here a 4 by 6, so we have 4 rows by 6 columns. And if we have 3 pivots, 3 pivot rows, 3 pivot columns, then we're going to be left with 1 row and 3 columns, just to think about that. So we're left with 3 non-pivot rows, or 3 non-pivot columns and a non-pivot row. And we're interested in the dimension of the null space of A, so we care about the columns here. And, well, it's just going to be 6 minus the 3. So these 3 columns are each going to be a null dimension. And the dim null A then equals 3. And you could think of that as just being 6 minus 3. 6 for the number of columns. And then the rest of them, for parts 2 and 3, I would again just take the M and plug it in and see what you get. And obviously the dimension of the column space and the dimension of the row space is going to be the same for each of those. All right. So the last one here, we are looking at the practice exam now. So this is the part about linear transforms. So this actually comes from a couple different sections. And I believe it's actually listed in the answer key where these all come from. Here, let's just talk about this first. So we have this, this sheep thing. I actually wonder if I can select. Well, it's okay. Anyway, so all right, we have this transformation, right? We're taking sheep and we're flipping it in some way such that it looks like it becomes mirrored somewhat, like rotated, mirrored, and also compressed, right? Because it started off as an oval and ends more of a circle. And they want us to describe in a sentence what effect T has on the sheep. Okay. So it does a few things to this. First off, I'm just going to write the first 2 letters and we can see how they change, right? So first off, we have, the letters are normal. The first thing we're going to do is we're going to compress it. All right, so it's going to be compressed down more like this. And we don't know exactly by how much, really. It's hard to say because, we're just looking at a drawing. I would probably call this like 1/2. I think that's a fair guess. You don't really know how much, but I mean, I'd say this looks about twice as long as it is wide. 1/2 is usually a safe guess. So I'm going to type this so that it's easier to see. And I'm going to say maybe scale by 1/2 on X. Okay, so in like the X direction, so horizontally, we are scaling it down 1/2. There we go. All right, so that's the first thing. All right, what next? I guess we probably want to get our rotation. So how are we going to be rotating this? I'm going to say, well, it looks like there's a flip that comes after. So I'm going to say it's going to look like that first. All right, so it's like, yeah, that looks good. Okay, yeah, so it's this is a rotation. Oh, I just did it. Right, this is going to be a rotation. We always want to think about this counterclockwise because it makes it easier when we go to the matrix. And this is just going to be a counterclockwise 90-degree rotation, right? Because we're just taking it and we're moving it 90 degrees counterclockwise. 90-degree rotation. Okay. Next up, I think we only have one more to think about here. Yeah, all we have to do is mirror this kind of over itself. If you notice here, the top part of the H is probably the easier part to look at, and that's kind of basically just flipped, and it looks like it's flipped over the y-axis if you think about it. If you thought about a y-axis with the H over here, we're just flipping it over the y-axis so that now the head of the H is over here. All right, so this is just going to be we will call it a flip over the y-axis. Flip over the y-axis. All right. Okay. All right, so part A asks you to describe in a sentence what effect T has on the sheep. So basically, it's just these three things. First, we're scaling it. Then we're rotating it counterclockwise. Then we're flipping it over the y-axis. That basically sums it up. And you can have a little drawing to go along with it to show what's going on. But yeah, that basically sums it up. So part B then wants us to write down the matrix for T. And since we're working in 2 dimensions here, we can safely just rotate this in, or we can just make T out of 2-dimensional matrices. All right, so first we need to think about what order do we want this to be in. And that's actually pretty important here because transformations have a weird order to them. You actually want to write the first thing you do, the furthest to the right, and the last thing you do is going to be on the left. So we're going to go from sort of last to first here. So the order that we wrote all these transformations in, we're going to go backwards. So our first matrix is going to describe the flip. Our second matrix is going to describe the rotation. And our third matrix is going to describe the scaling. All right. So now let's actually write them out. We have our flip matrix. All right, so we are flipping over the y-axis, and this is something that just comes out of the book. The flip matrix for being over the y-axis is just going to look 1, 0, 0, negative 1. All right, there's your first matrix. Our rotation matrix, this one is going to be trig derived. So maybe let's look at it over here for a second. All right, so it's going to be the cosine. Again, we're going counterclockwise, right? So it's going to be the cosine of 90, the negative sine of 90, and 90 is just because we're rotating at 90 degrees counterclockwise. The sine of 90, and the cosine of 90. And I definitely recommend putting this in your formula sheet if you don't think you have it memorized, because it's a good one to know for basically any time a rotation comes up. All right, and if we actually do the math out on this, what do we get? Cosine of 90 should be 0, negative sine of 90 should be negative 1, sine of 90 is 1, cosine of 90 is 0. So there you go. All right, we have our rotation matrix. So 0, 1, negative 1, 0. Oh, I messed that up. 0, negative 1, 1, 0. Okay. Let's see. We also need our scaling matrix now. So, all right, and we're talking about scaling in the x direction, right? So the only thing we need to worry about is this 1/2 in the x thing here, and everything else is going to be just the identity. So that is your scaling matrix format. All right. And I'm not going to do it right here, but if you multiply this all out, you should end up getting 0, 1, 1/2, 0. 0, 1, 1/2, 0. All right, and that'll be your transformation matrix. Okay. Next, let's move on to part C. Part C asking us about the area. So area should immediately make you think of determinants, because determinants are kind of this link between matrices and area of with geometry. So we have a formula somewhere in the book that says the area of something, we'll just call it S. I'm sorry, the area of TS equals the absolute value of the determinant of T, so your transformation matrix, times the area of S, whatever your original shape was. So we had some shape originally, and we did all these operations to it. We want to know how did it affect the area. Now, intuitively, we know that it did impact the area somehow, right? Because we started with an oval and we ended with a circle, so we probably did something. And if we want to know exactly what we did, then it would be a good idea to look at the determinant. So we'll take the determinant of T. The determinant of a 2 by 2 is just going to be AD minus BC, remember? So this is just going to be 0 minus, and then BC is 1 times 1/2. So this is going to be 1/2. Take the absolute value, and you should just get 1/2. So what this says is that the area of our new shape or our new image is half the area of the old image, and the determinant told us that. Finally, we have part D. So part D asks, assume instead the first image is centered at the origin and the second is centered at 1, 0. Write down a matrix for T using homogeneous coordinates. So just to review, when we do homogeneous coordinates, we are basically taking our 2x2 matrix, so whatever our 2x2 matrix is, we can turn it into a homogeneous matrix by keeping those same four things, and then adding 0, 0, 1, 0, 0. And this 1 down here acts kind of like a multiplier. It tells us how we're scaling it. Also, what it can tell us, what this kind of matrix can tell us, is it lets us do these transformations. So say we wanted to shift this over, we would just change this to get x to shift and change this to get y to shift. So it gives us that ability. And we're going to actually do that here, right? We're shifting this thing over 1, 0. So if we want to shift our matrix T, which we had written was 0, 1, 1/2, 0, and we want to turn it into a homogeneous matrix that does the same thing except shifts it over 1, 0, then we're just going to put the numbers back in here. And over here, remember, x is going up 1, so we put that. Y is not going to change at all, so we keep 0 there. And the bottom row can just be filled in 0, 0, 1. And there you have it. So this is your final homogeneous matrix that does all the same things, and then at the end also translates. So you could imagine a separate thing being in here that translates this, I guess it'd be over 1 in the x direction. So this does 4 operations to this thing. And that's about it for that problem. And that's all I have for you guys. So I'll see you all next week.